Welcome to Cookie's Maths and Science Hub. Today we'll be exploring some of the trends on the periodic table. As we've discussed, the periodic table provides us with a vast array of information. An important part of this information is the trends that it can show us, showing the differing properties of elements relating to their reactivity, their electron structure, and a vast wide range of different factors as well. Let's explore some of these now. Electrons in the outermost shell of an atom, or the valence shell of an atom, are called valence electrons. Now, the important thing about the periodic table for these is that the number of valence electrons of an atom is equal to the group numeral of that element for the first 20 elements. It gets a bit more confusing after that. But effectively, this is where we use our Roman numerals. So if we were to look at Roman numeral 6, for example, we could look down and go, oxygen and sulfur both have 6 valence electrons. Now, the number of electron shells, on the other hand, that is how many shells there are of electrons around an atom, is equal to the period of that element. So once again, looking at oxygen, we can say it has 6 valence electrons. And if we go down the rows, remembering periods are our rows, we go 1, 2, oxygen has 2 shells. So it has 2 shells and its second shell has 6 valence electrons. Whenever you have multiple shells, it assumes the shells before that valence shell are full. So in oxygen, we'd have a shell of 2, then we'd have a shell of 6, which you can see adds up to 8, which is our atomic number, meaning our oxygen atom is neutral. So once again, let's look at another example now. Let's go, group 2, or Roman numeral 2, remember? So we have, calcium, for example. We must know calcium has 2 valence electrons. Now, calcium's in period 4, so it's going to have 4 shells. So we know then it's going to have a shell of 2, 8, 8, 2. If you're still a little bit unsure about that and how the shells work, I suggest checking out our atom video to look more at electron structure. The reactivity of an element is determined by its electron structure. Now, because of the vast differences between metals and non-metals, we're going to look at them slightly separately. Metals become more reactive as you move to the left of the table. This is because metals want to get rid of electrons, and as we move to the left of the table, they have less valence electrons, meaning it's easier for them to get rid of less electrons. Now, metals become more reactive as you move down across the periods. This is because as you move down, we get more shells, correct? As we've just established in our electron trends. So more shells means those outer electrons are further away from our nucleus, which is keeping them in close, meaning it's easier to get rid of those electrons from further away. Think about it this way. If you're holding something and you're holding it at arm's reach, it's going to be harder to hold on to than if you're holding it against your chest. So because they have more shells, those electrons are further away, it's harder to hold on to them, making them more reactive. Non-metals, on the other hand, yes, they still react based on their electrons, but they want to gain electrons, which effectively means the trend for non-metals is reversed. Instead of becoming more reactive to the left, they become more reactive to the right of the table. This is because their valence shells are more full, so it's easier for them to pull in just one electron than multiple electrons. Now they become more reactive as you move up the periods, again, for the opposite reasons. Because they want to pull in electrons, it's much easier when they have less shells. Because if they have less shells, they're going to more easily pull in those electrons. Think about it again. It's easier to grab something that's right in front of you than it is to grab something on the other side of the room. So it's going to be much easier for them to grab electrons when they have less walls or shells between them and the nucleus. These ideas that we've just discussed about reactivity can be really summed up with our atomic radii trends. The atomic radius is defined as 1/2 the distance between the nuclei of identical atoms that are bonded together. And effectively, it allows us to see the size of an atom. The radius of atoms decreases across the groups from left to right. This is because if we have more protons, it's going to pull everything in closer together. So think about it this way. Lithium, for example, on the left-hand side of the table, only has 3 protons, whereas fluorine on the right-hand side of the table has 9 protons. It's going to have much more charge to pull everything in closer together, such as the electrons around the outside. Now, the radius of an atom increases as you travel down the periods. This is because as you move down the periods, there's more shells. More shells, bigger size. Makes pretty clear sense to me. So, remembering it decreases from left to right and increases traveling down. Now, some people find it difficult to do decrease, increase and prefer just increase, increase. So in that case, you'd say it increases from right to left and increases as you move down, or decreases from left to right and decreases as you move up. Whatever works for you to remember those trends. Electronegativity measures an atom's tendency to attract and form bonds with electrons. This property exists due to the electronic configuration of atoms, that is, the positive charged protons and the negative charge of electrons. Now, again, this relates to the size and structure of the atoms, as that is how the periodic table is set up. So electronegativity increases across the groups from left to right. This is because as we move to the right-hand side of the periodic table, there's more protons. More protons means it's going to be easier to pull in electrons. Electronegativity decreases as you move down the periods. As the shells get bigger, it's going to be more difficult to pull in electrons as the protons are further away from the outside of the atom. Ionization energy, on the other hand, is the energy required to remove an electron from a neutral atom in its gaseous phase. Conceptually, it's effectively the opposite of electronegativity. The lower the energy is, the more ready the atom becomes a cation. So effectively, this is getting rid of electrons, whereas electronegativity is gaining electrons. So the trend, as you would guess, is pretty much the opposite. Ionization energy increases across the groups from left to right. As you move to the right, it's going to require more energy to get rid of electrons. Ionization energy decreases as you move down the periods. As you move down, your atoms get bigger. It's going to be easier to lose those electrons as they're further away from that central nucleus where the protons are. Now, as I've stated, ionization energy conceptually is different than electronegativity, but you'll notice the trends kind of line up more than you'd think, even though we talked about them being opposite. This is because ionization energy is the energy required to remove an electron. It's not the energy that we lose when we lose an electron, it's the energy required to remove an electron. As such, high ionization energy often goes hand in hand with high electronegativity. Electronegativity, remember, is the tendency of an atom to gain electrons. Therefore, if it has a high tendency to gain electrons, it's going to require a lot of energy to lose electrons, which is our ionization energy. Thanks for watching. Hopefully now you have a good understanding of the trends on the periodic table. Be sure to subscribe to the channel for all future maths, science content. Hope to see you again soon.